Okay. So we have been discussing symmetric Fock spaces. So let's start with that. And HB any Hilbert space, complex Hilbert space. Okay. Then we defined gamma as H. Sometime we will write just gamma of H when we are not using any other Fock space. We are using only symmetric Fock space. So we may call it just gamma. This S is for symmetric, but we may just call it as gamma of H. Okay. So symmetric Fock space. Fock space, which is just which is defined as C direct sum, H direct sum, second tensor direct sum, H Sn direct sum. It's an infinite direct sum like this. So this is what is the symmetric Fock spaces. Then we want to define. See, there are two kinds of vectors which are useful vectors in this. One is what are called finite particle vectors. So these are what are called finite particle vector space. H symmetric n. That's a finite particle vector. See, it's like if you have n identical particle, which you can't distinguish between them. Like, of course, they are all subatomic particle, like electron or photon or something, photon kind of thing. Then this is a framework for that. Okay, they cannot be distinguished. That's what it means by you apply a permutation and it's the same thing. Okay, so they are called finite particle vectors, finite particle Hilbert space, and so there are finite particle vectors are there. So you can define, if you want to define an operator on the symmetric Fock space, you can define it on each finite particle vector space and show that it exists. I mean, it has a norm on finite particle vector space. The supremum of the norm is less than infinity. Then you can say that it's a bounded operator. That's one way of doing. The other way is you can define something on some particular kind of vectors called exponential vectors. Okay? This is the other way of doing, and that's what we will use now. Finite particle vector will come later. So we define if U is any vector in H, then we defined E of U in the Fock space as follows. Okay, which is E of U is just, so there is in the complex vector space, there is one, there is a phi is equal to 1 in C. Okay, phi is one direction. I mean, the number 1 in C is what is called the vacuum vector. This is what is called vacuum vector. So, okay, vacuum vector is phi. We call it phi, and E is just phi direct sum U direct sum. You can take the n tensor, which is invariant under the action of the symmetric group. So sorry, this is not the thing. This is U by 2 factorial square root. Otherwise, it's unbounded. Okay, I mean, you have to sum it, and the sum has to be finite. So okay, n factorial square. Then we have E of U. This is defined for every vector U exponentiate vector. If you have any vector in the Hilbert space, then you can exponentiate that vector to this exponential E of U. This is very similar to the exponential, or usual exponential, except that we are putting a square root in the bottom. Usually it will be n factorial. We are putting a square root because we want to get this formula. You can put just, I mean, you can define it the other way also, work with that. But this is very convenient. This formula is very convenient. E of U, E of V. If you take the inner product, we computed the inner product last time, and that is equal to E of the inner product between E and V. It's for this reason we are defining it like that. So this formula holds. Okay, so that is why it's called exponential vectors. So this we proved, and we also proved this mapping U going to E of U. Okay, this is in H, and this is in gamma S of H. Okay, this is continuous. Both are non-linear space. You can talk about continuity. And if Un goes to U, then E of Un will goes to E of U. Okay. So this map is continuous. This also we prove. Now we want to prove something else. We want to prove that this family E of U is a linearly independent family and it's a total family. So if you want to define an operator, any operator, you can define it on the exponential vectors just by any function. This is a linearly independent. So when you are defining an operator something, then you have to work out whether it is well defined, because same vector can be written as two different linear combinations, and then you have to verify whether it is well defined or something. But when they are linearly independent, there's one way of writing it. The linear combination can be written in one way, so you don't have to worry about well defined. So if you have any function defined on this E of U, I mean, E of U means it's a function on H, of course. If you have any function, need not be linear, any function, then you can have a you can have a linear operator on the span of E of U. If it is bounded there, then you can extend it to the whole symmetric element space. Okay, or if you define any operator on this E of U, any function on E of U, and suppose if it preserves the inner product, then you can, we have the lemma, and we can extend to the unitary and the whole of the symmetric Fock space. So that is another thing. So that is what we are going to do now. We want to define unitaries on this. Okay. So for that, we want to prove the following proposition. This set E of U, which we write it like this, E of U, UN. Usually, this is not, this has to be span of this. Or we have to, usually E is called the span of E of U. So let's just call it E, capital E or something. Okay. E of U, U in H, okay, is linearly independent, is a linearly independent set and total in the symmetric Fock space. Okay. Proposition. There is some messy calculation. I will leave it as an assignment. Okay. There is something. So, okay. Anyway, I'm not in a mood now to do that calculation. Okay. Okay. So first thing is linearly independent. So what does it mean by linearly independent? First thing is linearly independent. First, we will check the linearly independence. So suppose lambda 1 up to lambda n, some numbers, complex numbers. Then we want to suppose summation lambda I. Summation lambda I and U1 up to UN, U1 up to UN. We want to show that if you have any finite linearly independence, if a set is linearly independent, it's an algebraic statement. Okay, so if you have, it's not, it's not about, you don't consider infinite family. You take a finite family, U1 up to UN, and finite numbers, lambda 1 up to lambda n. Okay. Then this E of UI, I equal to 1 to n, equal to 0. We want to show that each lambda I should be 0. That's what we want to show. Suppose this is equal to 0, and we want to show that lambda is at 0. So this is 0. So now this implies E of lambda U, okay, summation I equal to 1 to n lambda I E of UI. This is equal to 0 for all lambda in C and for all U in H. Of course, if something is 0, then its inner product with any vector is also 0. Okay. Now this is equal to exponential. We know we have the formula, which is this is equal to, you can take the lambda out, and you can take the lambda out, and the lambda j is here. Lambda j is out, of course. Lambda I, summation I equal to 1 to n, summation lambda I, the lambda is here. Then this is just U, Uy. Okay. This is equal to 0. Okay. This implies this is equal to 0. Okay. This is true for all lambda and for all U also. Okay. Now you want to choose a U. Okay. See, the point is this. Okay, fix I. For we let us take this set. Sure. Lambda bar. Okay. This is okay. I put a lambda bar here, so it's true for all lambda. Okay, you can work with lambda bar also if you want. Okay. Okay. Now I want to choose U so that these are all different functions. Now we have got some relation in terms of function, exponential function. This is true for all lambda. Lambda is are fixed numbers. You have to show that they are equal to 0. I mean unknown numbers, but still fixed numbers. This is true for all lambda. And U is also for all U. Now I want to choose a particular U so that these are all different. The first thing is this Ui for a fixed I, this set is closed. I mean all those U in H. Ui equal to 0 is closed, of course. Okay. This implies U in H, Ui not equal to 0 is open, of course.
It follows from the continuity of
exactly, continuity of inner product. Correct. It follows from the continuity of the inner product. So now, since inner product is continuous. So now this is not equal to 0 is an open set and is also a dense set. Open and dense. Why is it dense? This is equal to all those. This is just, I mean, Ui is not, sorry, I don't want that. Sorry. Okay. Actually, I want to define a different set. Sorry. Slightly, I mean, I want to use this, but I want to say something different. Sorry, I will erase this. I want to take an ij. Okay. Okay. From whatever we have discussed, this is true. Let us define a set Sij is equal to all those U in H such that Ui is not equal to Uj. Okay. I is not equal to J2. Okay. Is dense, is open and dense. Why it's open and dense? It's open is this is exactly equal to Ui minus Uj. I mean, this is just inner product with Ui minus Uj should be 0. So this vector, you take this C, multiply by C. This is a one-dimensional vector space. This is a perp of this. Okay. And any vector space which is not any so perp is this is a closed subspace, right? No, this is not perp of this. Perp complement, right? Yeah, perp complement. I mean, this is not equal to this means this is just the complement of that is equal to that. That means Ui minus Uj equals 0. The inner product between Ui minus Uj is 0, which is just the perp of Ui minus Uj perp. Its complement. Okay. So if you have any, see, if you have a closed a subspace, a Banach space, if you remove one dimension, one vector, it's just this is just a Hilbert space where the one dimension is removed. A set is removed, not a vector space. If you remove a one-dimensional vector space, that is going to be that perp. It's not even that. I mean, that perp is one dimension removed. It is just the complement of that. For example, so if you have, it is just a complement, which is like, if you take any subspace, closed subspace of any Hilbert space, if you take any closed subspace, proper closed subspace, then the complement is nowhere dense. No, that subspace is nowhere dense. Sorry. Any closed subspace of a Hilbert, so this is because any closed subspace is nowhere dense. So the complement is open and this is because any closed subspace, any proper closed subspace of a Banach space. You can take a Banach space or Hilbert space, whatever. Okay. The Banach space is nowhere dense. You know what is nowhere dense? It does not contain any open ball. Okay. Nowhere dense means something which is closed and then it does not contain any open ball inside that. Okay. So the complement has to be dense and open. Of course, this is closed. The complement has to be open. And so why is this nowhere dense? That is because if you take any open ball, suppose if you have any, so suppose, let me consider any x and x be any Banach space. I'm giving the proof of this statement, okay? X naught contained in this X is closed subspace, okay? Then if you have any U naught in H naught and R greater than 0, okay? You want to say that this ball B of U naught R intersects with the complement. That's what I want to say. The complement, that it cannot contain any ball inside that. That's what Nova dense means. So if you take any ball, that will intersect with the complement. Okay. So you take this ball, this U naught plus epsilon times U, where U is in the complement. U is in the, you can take the perk or something. U is just in the complement. It's not complement. H naught or X naught, X naught. So X naught complement. Okay, where for epsilon is less than R. Then this is in that, right? Because U naught plus epsilon U minus U naught is equal to epsilon. Say you take a U such that norm U equal to 1. Okay. And this is equal to norm is equal to epsilon. U naught plus epsilon U minus U naught is norm epsilon times U, epsilon times U, which is norm is epsilon, which is less than R. So this is there.
This would be true like arbitrary topology.
Arbitrary topology, but you have to have norm and everything. This will be true.
No, you don't need a norm. That's what I
Yeah, you don't need a norm. But from this, it's clear. Possibly you will have with locally convex or something. Yeah. So this is okay. Yeah, this will work for anything. Okay, so this is clear now. This is what no valence means. This is equal to less than epsilon. So this is in, because this U naught plus epsilon U is in that open ball. Okay, that open ball, that U naught plus epsilon U is not in the vector space, because U naught is in the vector space and epsilon U is outside the vector space. So the sum will not be in that. Okay. See, it is like this. If you have two-dimensional vector space, you take any ray. Sorry, it should pass through origin. So if you take any ray, you remove that ray, then the complement is the orthogonal complement is one-dimensional subspace. That is not a thing. But if it's a set complement, that will be dense. Okay, that's all. So we are taking the set complement. Okay. So it's because of that you have, if you take any closed subspace, its complement is dense. So here you are removing one dimension. Okay, it's an infinite. That perp is an infinite dimensional subspace which is closed, but still it is one dimension less. Whatever. I mean, it does not include one dimension. So the complement is, even though the orthogonal complement is just one dimension, the set complement is dense. Okay. So we have that set is Sij is open dense. Okay. Now Sij, this set Sij, I not equal to j, and Ij less than or equal to n, greater than or equal to 1, is a family. It's a finite family. Family of open and dense subset. Okay. For each Sij is open. So I'm just saying that this family is open dense. So the intersection will also be open and dense. Actually, if you have a countable family of open and dense subsets, then the intersection also open and dense. That's what is bare category theorem. You must have seen. You can use that if you want, but you don't need it when it is finite family. You can directly say, if you have an open dense subset, if you have another open dense subset, since it is open, it has to intersect. If you have something dense, every open ball will intersect. Then the intersection is again open. Okay, which is again dense. Okay, so when you intersect with the other one, you go on doing that, you will get a, okay, it's clear that it's open and dense. Okay, so if you have a finite family of open and dense, it should be two dense subset need not even intersect. Okay, rationals and irrational, they don't intersect. Okay, but if it is open and dense, it has to intersect. Okay, so their intersection is this. So if we have S is equal to, so there exists a U in the intersection of this Sij. I not equal to J and Ij less than or equal to N greater than or equal to 1. There exists a U. And it is so for this U, and for this U, Uy is not equal to Uj. For all Ij, I not equal to J and Ij less than or equal to N greater than or equal to 1. Okay. Okay. So why am I doing all this? We just got a U such that Ui is U inner product with Ui is not equal to Uj. Okay. So let some theta j equal to Ui. Okay. Then this e power lambda theta j are different functions. Okay. Lambda going to these functions or lambda or whatever. Lambda going to lambda is these functions. You know that exponential functions, are different functions. Are linearly independent for when theta j is not equal to linearly independent as functions. Do you know this? Exponential functions are linearly independent as functions. It's very easy to prove it. It is like, see, if you differentiate a linear, this is a function of lambda. So if you differentiate it, you will get theta j as this eigenvalue. And eigenvalues of any operator, but this is a Banach space of functions. This is not clear. They have to be linearly independent. That is one way of saying it. Eigen vectors should be linearly independent. Or we can do something else. So these are all linearly independent for j, for different j's. That's what I'm saying. For j less than or equal to n, greater than or equal to 1. So you want to show this? We can even show this, for example. You want a proof of this? Or shall I leave it? Okay. So, you want to show that this is true by induction, we will show. For n equal to 1, if there is only one function, there is nothing to show. Oops. The n functions, if it is true for n functions, okay, we have to show it for n plus 1 functions. Okay. So suppose this is true, proof by induction. Okay. So suppose true for j less than or equal to n greater than 1 for n functions. Okay. And suppose we have lambda 1 up to lambda n plus 1 such that summation lambda I e power lambda some theta j. No, we want to say we want to talk about we want to talk about e power lambda j. No, we want to talk about theta j. No. What do you want to show? We want to show that no, the idea I have will not work. I thought if you differentiate, you'll have, but you have to take another alpha, some other alpha I, summation alpha I, that should be true.
Take any linear combination, differentiate n minus 1 piece. Then you will get a system with Vandermonde determinant, which is non-zero since theta I j are not equal.
Yeah, but you have to use some other funda, no? Then how will you show? You have a system of equation, which will show that if you have some alpha 1 plus alpha n equal to 0, then some other, you will have n set of equation. You have to work on that. I thought there is a easier way of, anyway, we assume this, okay? This is a well-known fact. Let us not waste time on this, okay? This is a well-known thing, okay? Now, by differentiating only, I want to show something, but okay, it's an exercise. But what we have here is, we have something. So we have got this. Okay. Summation lambda times. So this is, I call this uy equal to theta j. Okay. So let ui equal to theta I. Then the function summation lambda I. Then the functions summation lambda theta j, theta I are linearly independent. Okay. Is linearly independent. So we have already got that. So this implies lambda I equal to 0 for all I. Okay. That's right. So this implies E of U1 up to E of UN is linearly independent. Okay. So is linear as vectors. Okay. So we have proved that exponential vectors are linearly independent using the fact that the exponential functions are linearly independent for different constants. Okay, e power lambda theta. So that proof you can check somewhere. Okay. Okay. Now we want to show its total. Okay. So totality. For that we do the following. To show e power u in h is total. So you have to get every vector in a finite particle space, finite symmetric tensors. You have to get any vector from there. Okay, that's one thing. So first we show that. First we show the following. See, first it's clear. Phi, the exponential vector is nothing but E of 0. Okay, it's just one direction 0, 0, 0, 0. So this is in gamma SH. We got E of 0, which is phi. Now, if you want to, how do we get U? So if you have E of U, okay, minus E of TU minus phi divided by T, limit T going to 0. I'm just differentiating. E of 0 is phi. E of 0 is phi. Okay. And then I'm just differentiating it. This is nothing but nothing but d by dt of E of TU. Okay, this function at t equal to 0. Okay, I'm just differentiating. So, which is just, it's a direct sum starting with phi. So you have removed the phi. Okay, and then you have, so it will start with TU tensor 2 tensor, TU 3 tensor, it will be like that. Okay, but you are dividing by t. So it will become U direct sum TU tensor 2 direct sum T square U tensor 3 like this. It will go like this. This is equal to U as T going to 0. Okay. Huh?
It starts with 0 direct sum U direct sum.
But the 0 E phi I have taken it up. Phi is removed.
So how does it get like U is a thing in H, right?
E of TU is phi direct sum U TU direct sum T square U square.
Phi minus Phi should be 0. So we
Correct.
shouldn't be like 0 direct sum U.
Yeah, it will be 0. 0 divided by anything is 0. What is the problem?
No. Okay.
You are not dividing in the denominator. You are dividing in numerator. There is no problem.
Like I was concerned about the expression, like how
yeah, 0, you have U. Everywhere else 0 you will get. When T going to 0, everywhere else 0. So the finite particle vector, I mean, U, when I say U, it is 0, U, everywhere else 0. That's what I say as U. So you got the U. So you know that first particle vector space, you get it by differentiating. Now by differentiating n times, you should be able to get nth particle vector space. But then you will only get U tensor n. From U tensor n, you have to get any finite particle. Any finite symmetric tensor. Okay. Now, I am saying that you take ETU, the same function. Okay. And then you remove up to n. So you got the first particle vector space. Suppose you have got n particle vector space, you have to get the n minus 1 particle vectors, right? You go on like that. You assume that, I mean, we want to prove it by induction. Okay. You can, by this process, you can get it. Suppose, I mean, you got 0th particle vector space, you have first 1 particle vectors, and suppose you can get up to, suppose U tensor n. You get it, I mean, suppose you get, let me just write the formula for U tensor power n plus 1, okay, which is ETU minus summation n equal to 0 to k equal to 0 to n, okay, U tensor k divided by k factorial square root. Of course, you remove the n particle out, okay, and you should remove TU, right? No, that is for t equal to 0, right? That's okay. You should have a t or you shouldn't have a t. Then you should remove t. Okay, t power k also. Okay. Then you divide it by t power n.
The top expression you will have like TU divided by root 2 factorial. Like
Top expression, this top expression.
let's scroll up a bit.
Here,
No, on top. Like you direct some TU.
which one? First, the
On top.
Very top.
The limit.
What will you have?
You direct some TU.
Yeah. Sure. You will have that. This is what you are saying.
Yeah. So like then when you subtract it, you will like.
No, as t going to 0, that will go to 0. That's all.
Yeah. No, so now you have an expression for U tensor n times or. Okay, yeah, that's.
No, that is only I'm saying the 1 particle vectors you get it like that. I missed the denominator part. You have to put the denominator part. Okay. 2 or 3 factorial square root or something, but you'll get it. So I'm saying that the n particle you can get it like this. E of TU. Okay. And the summation k equal to 0, you remove the first n particle from there. Okay, k equal to 0 to n. Okay, then you divide it by t power, then the n plus 1 particle, it will start from n plus 1 particle. You divide it by t power n plus 1. Okay, then limit t going to 0. This will give you tensor n plus 1 divided by square root n plus 1. Because as t going to 0, the other vectors, only the n plus 1 particle, there will be no coefficient of t. Everything will have a coefficient of t, which will go to 0 because of that. So you will have only the n plus 1 particle, which you will get it like this. Okay. So from E of U, using E of U by taking linear combination of E of U and taking limits. We are taking linear combination of E of U. N plus 1 factorial, you are right. Of course. Yeah, n plus 1 factorial, right? Yeah. Did I, in the definition also, did I write n plus 1 factorial? Yeah. Yeah. So using exponential vectors by taking linear combination, by this, by taking linear combination and by taking limits, we are able to get the U tensor n. Okay. Now from this U tensor n, you have to get any symmetric tensor, which I leave it as an assignment. Okay, which I will tell you how to do it. Okay, this is assignment. Rest assignment. So prove U1, this symmetric tensor U2 to UN is in the span closure of E of U. Okay. U in H. So how do you do that? So let me tell you how to do that. One way is there is a formula like this, which you can try and prove using induction. Okay, U1 up to un.
Do we need the closure in this?
Yeah, you need closure because you are taking limits, no?
No, like it's finite. No, the U tensor itself is not there in the. Oh, okay. U tensor is.
Yeah, yeah. Now U tensor in, you can get it from, I mean, by doing something, by some algebraic manipulation, you get it. So there is this formula, I think I remember correctly, 1 by 2 power n summation epsilon I equal to plus or minus 1 and epsilon 1 up to epsilon n and summation and then epsilon 1 u1 plus up to epsilon n un. Tensor n. You take this sum where you vary all this epsilon I. It will be easy to see that this is true for n equal to 1, n equal to 2. It's very easy. So if it is true for n equal to n, you have to prove it for n equal to n plus 1. This is one way of doing. In KRP book, if you see there is something is written, you can look at that. There he says that you can take something like this. I mean, so you know what is I already given an assignment where you can write the orthonormal basis of the symmetric finite tensor, which is actually given by ei1 power r1, ei1 power rn, where r1 plus r2, the sum of the ri should be equal to that n. Okay, this is true for each of them. Okay, now if ei is any orthonormal basis, alternate method. Alternatively, okay, O and B for this H, okay, then you can take Z1 EI1 plus ZN ZK or ZK EIK. Okay, you take something like this and you take this tensor n. Okay, then you will get a polynomial in Z1 up to ZK whose coefficients are vectors. You consider this as a polynomial in this. Okay.
What we need to show?
You have to show that all this, each of the EI1 is there. It's not EI1. This is equal to summation Z1 power I1, sorry, R1. Maybe I'm giving the full proof. Z2 power R2 up to ZK power RK, where R1 plus R2 plus RK equal to n. Okay, here you will get EI1 tensor, EI2 tensor something. That's what you will get. You will get some vector here. Okay, and so you want to get that vector, symmetric tensor of that vector. Possibly you will get the symmetric tensor itself here. I think when you sum it over all of them, you will get the symmetric tensor there. Because you are going to get different Z1 power R1. No? For a fixed one, it will be arranged in something, but you want to collect all the Z1. You will get the symmetric tensor of EI1 up to EIN, not EI1 power R1, okay, and EIK power RK. You get that symmetric vector here. You compute what you get here, which will be symmetric tensor here, whose coefficient is this. Okay, now you have to get each one of the symmetric tensor from that, using that. And do some different, you can do something. This is true for all Z1 or Z. Use some idea to get that symmetric tensor. Okay. Okay. So that is the assignment. Okay. So this will prove that this is a exponential vector for total. Okay. If you are okay with this, I will go to the next proposition. Of course, as I said, any Hilbert space, any two Hilbert spaces are isomorphic as far as it is infinite dimensional and separable. But we want to identify in a particular way. So there is a way of identifying. See, this is gamma. The symmetric Fock space is like an exponentiation. Exponentiation means what? It will take sum to product. Okay. E of x1 plus x2 is E of x1 times E of x2. Okay, as a function. This is you are exponentiating a Hilbert space. Okay. So there exists an isomorphism. There exists a unitary. Between gamma HK are two Hilbert spaces. Write it again. I'm going to write the same thing. HK, two Hilbert spaces. Yes. Then gamma of there exists a unitary between gamma of H direct sum K. Okay. You can take direct sum of two Hilbert space to gamma of H tensor gamma of K. Okay. You want to call that unitary something, maybe a U from here, such that U of E of U direct sum V equal to E of U tensor E of U. Okay. I mean, the unitary is defined, but it is defined on total set. Okay. So you have to show that it preserves the inner product in the total set, so it will extend to unitary. That's all. So it is through this unitary we identify gamma of H direct sum K to gamma H times gamma K. Okay. I mean, as it is, they look like two different Hilbert space, but we identify those two Hilbert space using this unitary. So whenever we write, we will not even say that the unitary. We will identify with using this unitary these two Hilbert spaces. We will treat them as same Hilbert space. Gamma H tensor gamma K is gamma H direction K. Okay, you will write it later. There is another way of doing it also, using finite particle space also you can write this tensor. It will be the same operator, but this is better. So the proof, we only have to verify it preserves, this map preserves the inner product. Okay, so E of
Is it true for other Fox spaces also?
symmetric for anti-symmetric Fox space, it's true, but there is no exponential vectors, but you have to give a different proof. In KRP book, it's there. We will not discuss it. Free Fox space, it's not. I said in the beginning itself, it's too big. It will contain the tensor, but it will be bigger than that, much bigger than that. Okay. So now we only have to verify. We verify this E of U1 direct sum U2 V2 V1, E of U2 direct sum V2. We just have to verify what is this inner product. I mean, we have this set E of U direct sum V in H direct. I mean, V U direct sum V is in H direct sum K. E of that is dense there. Okay. Similarly, we know that E of U is total in gamma of H. E of V is total in gamma of K. Then if you have two total set, then the tensor of the total set, elementary tensor of the total set is total, that we have seen. Okay. So because of that, this is also a total set. So this map, whatever E of U direct sum V to E of U tensor E of V is a map from total set to total set. If they preserve inner product on that, it will extend to unitary by our lemma. Okay. So we verify that it is a map between U is a map between total sets. Okay. Total sets. Okay. We only have to verify it preserves inner product by our lemma. So this is equal to exponential. I mean, this is e power. That's what I'm writing it. It's a function. Okay. By x, I mean the function. E of U1 direct sum V1, U2 direct sum V2. Okay. This is equal to exponential of U1, U2 plus V1, V2. This is equal to exponential of U1, U2, exponential of V1, V2. But then we know that this is equal to E of U1, E of U2, E of V1, E of V2, which is same as U of U1 tensor E of V1, E of U2 tensor E of V2. Okay. So it preserves the inner product. Okay. and it extends to U. Okay. Okay, it's fine. So Fox space takes direct sum to tensor products. Okay. Final thing is we want to define some very important class of operators on this. Okay. Okay. These are what are called, see, in quantum mechanics, you convert some observable as operators. Okay, something that is what is quantization is. It's just a model. They are not actually the operator. Observable is it's like model for operators. Okay, you work with that. That is what first quantization. Then if you have some other representation of that, that's called second quantization. So we have unitaries in the Hilbert space. You have a H is a Hilbert space, and you have unitaries in the Hilbert space, which is first quantization. You represent that unitary group, which is a group, as operators on the Fox space. We will represent it now. This is what is called second quantization. Okay. Second quantization of unitary of H. This is the unitary operator, group of unitary operator. UH is group of, this is a group, of course. It has inverse, you can multiply group of unitary operators. On H. Well, it's just fancy way, but the definition is very easy.
From H to H.
H to H, you have unitaries. They form a group. Unitary, orthogonal group, all those things we say, no? In real unitaries are called orthogonal group. It's a unitaries group. Okay. Because if, I want to say that it's a representation of the group, if you want to use that language. Whatever we do is the representation of group. It will respect the product. Okay. So for U in U of H, which is a unitary, by U of H, I mean unitary. Okay. Unitary group. Define gamma U, okay, of E of, this is capital U, E of small u, okay, and U in H. Okay. Gamma U acting on E of U equal to E of U. Maybe I use a different vector. U is a vector, capital U is an operator. Okay. Gamma of U acting on exponential vector E of U is just E of U. It takes E of U, E of small u to E of UU. Okay. The image of that. E of U going to this. Then to verify this, E of UU, E of UV, okay, U and V in H. This is equal to, exponential of UU, UV, okay, by definition of exponential vector. But then they are unitary, so this is equal to UV, okay, and this is equal to E of U, E of V, okay. So they preserve the inner product. Okay. Gamma U preserves. Yeah, but gamma is gamma of U, which is the second quantization of U. If we want to use different notation, you can use. This is, gamma is used for the fact gamma of H is symmetric Fock space. Gamma of U is an operator on gamma of H. Okay. That's all. Preserves the inner product. It preserves the inner product on this set, on exponential vectors. Okay. But exponential vectors are linearly independent. That's not needed for unitary operators. It's a total set. So this implies extends to a unitary. Extends to a unitary on gamma of gamma S of H. This gamma, this is what is called second quantization of U. Okay? This is what is called second quantization of U, which I have written it here already. So
Why is it called second quantization?
because first quantization is the U itself. Okay? You are quantizing something. Second, whatever. This is just physics language. Okay? It has to do with physics. That U is the first quantization. So this is second quantization. So this is easy. So this is if you have so further. So you can define this for any unitary operator. So gamma of U1, U2 is equal to easily you can verify that gamma of U1 equal to gamma of U2. Because this relation is satisfied on the exponential vectors. Gamma of U2 is going to act the unitary operator inside the exponential. Then if you apply a U1, it will go again, it will be inside the exponential vectors. So this relation is satisfied on exponential vectors. So it will be satisfied everywhere. Some relation, algebraic relation is satisfied on a total set. Then it will be satisfied on all of, on a whole vector space. Okay. Because it's only extended linearly and through limits. And as far as these things are continuous, it's okay. No, we need totality or something. We need the strong continuity. Anyway, this is true. Let's just U going to see U is unitary. U is this map. You have this. Okay, let me write the proposition. From that it will be the proposition. See, there is something called strong topology, which I haven't defined. Strong topology is something the following. On B, this is true for any B of H. Okay. And a sequence of, strong topology is not a metrizable topology. You need nets actually, but doesn't matter. We will use only sequence for our purpose. Sequence will suffice. Okay. So if Tn
second quantization for the other operators.
Not every operator. Any contraction you can do. Any contraction you can do that. Otherwise, it's not possible. How you do this? You can take T power n. You can define it on the symmetric Fock space. It is precisely that. This okay. So it's a good question. Maybe I will discuss that and come to this. This also will come to that. See, if you have this gamma of U is nothing but U power 0 on the first particle vector and U direct sum and U tensor. You can tensor it. The second quantization exists in antisymmetry Fock space. It exists in free Fock space also. You can take U tensor here. Okay. U tensor, U square direct sum, U tensor n. It is basically this.
Wouldn't there be like the denominator is root?
No. This is for operators. See, for vectors in infinite direct sum, it should be square summable. For operators, it has to be just bounded. This U power n, that should be bounded. But all this U power n will have norm 1. Okay, so it will be bounded. Okay, so operators are, see, it is like any direct sum is like a L2 sequence. Okay, L2 sequence, it should be summable. But any operator is like an L infinity. It just acts in the left-hand side like this. Okay, so in an L2 sequence, you can act with the L infinity sequence. Operators are like L infinity. You have to imagine, it's not exactly L infinity. You can take any sequence of operators which is uniformly bounded. Its norm should be in L infinity. If you take the norm, then you get a sequence of numbers which should be in L infinity. it should be bounded. Then you can define an operator on the, that's what we discussed. Okay. So here everything will have norm 1. So this will be well defined. This you can do for any contraction. Suppose norm T is less than or equal to 1. Okay, T is in B of H. Then you can define T power 0 is just 1. Okay, then T tensor, it's like this. T tensor n will have norm less than 1. T tensor n will have norm T power n. Norm T power n. Okay, and which is less than or equal to 1. So though it will be an L infinity sequence. So you can define for any contraction. But if it's not a contraction, you can't do that. If it is greater than 1, it will blow up to infinity. You cannot do that. Okay, that's all. So any contraction, you can second quantize like this. Okay. So in particular, you are second quantizing like that. And we defined it on exponential vectors. Okay. You can define it like this also. Okay. Okay, we'll stop.
When you say U0, you mean it types as identity?
Identity. U power 0 is identity. Anything power 0 is identity. Okay. And the vector space power 0 is C. That's all. Okay, I will just define strong topology. Then I will define that also. Okay, if we have, this is true for strong. What happened? Okay, this is some new definition. So I will just define. So to define a topology, you have to define open set. Equivalently, you can define closed set. To define closed set, you have to say what is convergence. Okay, you define what it means by convergence, but you have to say convergence in nets. Okay, if you don't mind, I will use the net. Okay, it's just a different net. I mean, you can take it to be sequence. Okay, lambda in lambda contain a net in B of H. It converges strongly if T lambda xi converges to T xi, converges strongly to T. Okay, T xi for all xi. So that's all. It should converge pointwise. That doesn't mean it will need not converge in norm. Norm convergence is something else. It's like uniform convergence. It has, say, what is norm convergence? It has to converge uniformly inside the ball. Okay, on the unit ball. If it converges uniformly inside the ball, then it will converge in norm. It's like a uniform conversion. But it converges pointwise. For each point, it will converge. Okay, so this is a different topology. It's not a unbounded set, it's metrizable. In general, it's not a metrizable topology. So, but
it's like saying the evaluation maps are continuous. Right? The evaluation maps are at side.
Yeah.
Are continuous.
Evaluation map are continuous on what? On the T on B of H itself.
Yeah, on B of H. Like
it's not saying it is continuous. It is just saying for some particular set T lambda on it, it's continuous. Is that what you're saying? It is just T lambda is a net collection.
Yeah.
T lambda converges to T.
Like you can define continuity in terms of nets also. Like if every net converges to something.
The continuity of what?
Of the evaluation map at set. Like,
the evaluation map acting on what?
F of T is T of set.
No, I agree. But it's a map on B of H.
On B of H.
But it need not be continuous, no?
So like, if they are continuous, they reduce this topology, is what I'm saying.
Continuous means continuous with respect to what topology?
No, the
topology is on B of H.
Yeah. No, like if you assume they're continuous, then they use this topology. Like you pull the open sets from the image.
You take B of H, then you take this, then you define the topology to be
the inverse images of all open sets of the evaluation.
It is the topology which makes all those things continuous. Yeah, yeah, correct. It is given by that evaluation. It is given by those semi-norms if you want. For each xi, you will give a semi-norm and it's there. Yeah, correct.
Isn't it the weak topology?
The weak topology is you need you have to take the inner product. Okay. Weak topology is T lambda xi eta goes to it. Okay. Now this map is strongly continuous. So this is the proposition. This
Can you Goes to the definition.
It is just T lambda goes to T or Tn goes to T. If Tn xi goes to T as d psi for all xi, that's all. Okay.
So is that lambda in omega or?
Lambda is in lambda, capital lambda in lambda. As a net, it's a net. You can take it to be natural number if you want. You can work with sequence, okay? Just I want to write the precise definition, I use this, okay? For any bounded, uniformly bounded set, if T lambda in lambda is bounded, uniformly bounded, the norm is bounded, okay, then it's metrizable. Okay, you don't have to worry about it. Okay. So only when it is unbounded, you have a problem. Okay. So here unitary groups are bounded. Okay. It's a uniformly bounded set, non-bounded set. Okay. So there it's metrizable. Okay. So, okay, let's not discuss the topology. Point is this map. So this is from U of H. U in U of H going to gamma U. Okay. In U of gamma SH. Okay. Is strongly continuous. That is xi, and that is this map. Un goes to U. Okay. In it is strongly continuous. It is strongly continuous. Okay, let us see. UN strongly continuous means I think here also it's with strong topology and here also with strong topology, I think. Okay, strongly. Then gamma UN will converge to gamma U strongly. That's what I mean. Okay. So UN, so this implies UN converges to U strongly means implies UN xi goes to U xi for all xi. Okay. Then U of U, we have already seen that the exponential map is continuous, U xi for all xi. Okay. So this implies gamma UN acting on E of xi goes to gamma U of E of xi for all xi. Okay. Now we want to write it for any vectors, but when the net or sequence is uniformly bounded, this you have to work. This I should leave it as an exercise. See, if you have some Tn converges to T strongly, okay. Maybe I write the strong here. Okay, strongly. And supremum of norm Tn is less than infinity. I didn't mean that. No, not that. Tn xi converges to C T xi for all xi in S contained in H, which is total set. Okay. And norm Tn is smaller than infinity. Then Tn converges to T strongly. This is an exercise. You have to use the triangle inequality, use this. See, it is like, let me orally tell you the proof, you write the proof. Okay. The point is, I'm saying that if T and xi converges to T xi, that is what strong topology is. Suppose that happens on a total set, and this norm Tn is uniformly bounded, then that happens for all vectors. That's what this is. Okay. Suppose T and xi converges to T xi for total set of vectors, then it's true for any linear combination of that. Okay, there is nothing. So it happens on the dense subspace. Now you take any vector in xi, in any vector in H, then there's a sequence converging to that. For each sequence, each point in the sequence, this T and xi will converge to that. You have to say that it happens for the limit. You write the epsilon by 3 inequality. Okay, you write it as use triangle inequality, this minus this. Then you have to use the factor norm Tn is less than infinity. Call it some m or something, m times something. Use the epsilon by 3 trick and you will get that. Okay. Norm Tn xi minus T xi is norm Tn xi n minus Tn xi something through the limit, and I mean, this is the usual trick. Okay. So if you use that, you will get. So it's enough for a uniformly bounded sequence. It's enough to happen it for a total set. Okay. So here it is happening for this UN, it's happening for a total set. So that will imply that UN converges to gamma UN will converge to gamma U strongly. Okay. So if UN converges to U strongly, gamma UN will converges to gamma U strongly. So this map U going to gamma U is strongly continuous. Okay, so I want to define some important class of operators called Weil operators. Maybe I will define it and stop. We will discuss this in the next class. Okay, I will do it next.
The exercise is to prove that Tn converges pretty strongly, or if gamma is.
If Tn xi converges to null, from that it will follow. Exercise is if Tn xi converges to T xi for all xi in a total set, then Tn converges to T strongly. That is exercise. And it's uniformly bounded, then it's. I'm just saying Un converges to U strongly. Okay, then Un xi converges to U xi for all xi. That means E of Un xi will converges to E of U xi because exponential map is continuous. We have proved. That means gamma of U1 of E xi converges to gamma of U of E xi. Okay, so this convergence happens on a total set. By the exercise, it will happen for all vectors. Okay, which is by this epsilon by 3 triangle inequality and epsilon by 3 trick, you will get that. And you have to use the uniform boundedness. And these are all unitary, so norm is 1. Okay. So from that it will follow. So strong continuity will follow. Okay. Stop.
Why is it called strong topology?
Just like that. It is stronger than weak topology. There is a weak topology. It is just stronger than that. Okay. There is no other reason.